Yeah, I think we'll pair people. Is that the idea?
Even group code we can download and use one of the licenses from Untitled. But I mean, the easiest way is to group people to take or for. I think it's good. Otherwise, it will be work the less. Yeah.
So I think we ran a bit over, and we're constrained by lunch, which end at 1, I think. So let me be a bit faster than I would have liked. This is kind of an introduction to what we need for tomorrow about supervised learning. So there are different, learning is a big word. There are different types of learning. Here is only a partial list. Tomorrow we see some more. Today I'm speaking only about supervised learning. Okay, you have examples which are input, output, X and Y. You are trying to learn a relation, a model, a theory, a function that will allow you to predict new output for new inputs. And one of the themes, as we saw today, for learning is impostness and generalization. So you heard about impostness. I'll tell you more about generalization, which is another word for prediction, for predictability. And these are, so between today and tomorrow, you'll hear quite a bit about ideas that are at the core of this classifier, regressors, RBF, support vector machines, and so on, which are stuff that works. These are the kind of things that are used in many of the applications I mentioned earlier, like the Mobilize system. So I'll tell you only about the first two parts. The third one will be essentially tomorrow. Just some basic concepts on in supervised learning, and then just an overview, an idea of the foundational results. Some of them are quite philosophically deep, have to do, if one wants, about the nature of science and what is scientific. So the problem of supervised learning, as we said, you are given a training set, and that's a number, possibly very large, of input-output pairs. And your goal is to find a function which depends on the training set, so it change as you change the training set, which can predict Y for new X. Okay? Now, for this to be, does not always need to be possible. It may be impossible. There must be some relations between X and Y for you to be able to make some prediction. For instance, one counterexample I have, suppose I give you as inputs, names of people, and then as outputs, I give you their telephone numbers. And I can give you as many examples as you want. Telephone book after telephone. And I bet you cannot find an F that can predict the telephone number given the name, right? It's more or less completely random function. If somebody is willing to try the experiment, let me know. So that's a kind of notation. We assume that the training set is drawn with a IID, and so it's independent and identically distributed variables, random variables, and the identically is a crucial assumption. And there is a probability distribution, but you don't know it. What you have is only this training set, which depends on the underlying probability distribution, but in a way you don't know. So you don't know the probability p x comma y. If you know that, the problem would be solved. Okay? So you're trying to infer something without knowing this probability distribution, but only samples out of. You know, for instance, if you know this py of x, that's really what you'd like to know. Now, we assume there are probabilities in general, because even if the underlying process is deterministic, there is certainly noise in the measurements, or the underlying process may not be deterministic. So there are many different cases. For instance, suppose this is the deterministic relation between x and y, sinus wave. So if the probability distribution as for p of x, for your input part, as below, then this means you're getting many more samples where there are peaks in the probability distributions and very little elsewhere, or in this case, vice versa. And so there is always noise involved. For instance, you know, if you, let's see, let me use this backboard for a second. If you have, you know, a spring, and you have Hooke's law that the force depends linearly on the extension of the spring, then the probability of f given x will be a delta of f minus a of x, no noise. Okay? But if you have any noise, like additive Gaussian noise, then this probability will be a Gaussian in the error. So, there is a key thing you want to do in learning, which is you want to make predictions. You want to generalize. And this is kind of different from traditional explanatory statistics. Just don't simply, you're not happy just to explain the data, but you want to use the data to make predictions. The ability to generalize is also closely related to overfitting, to avoiding overfitting. And now, if I want to measure how well I'm generalizing, I have to first decide about how I measure the errors. And so, typical notations in machine learning is to use this loss function that measure the error between your prediction and the actual true value y. So, the usual loss function, the traditional one, the one we have seen, for instance, with Mahadevan before, is the square loss, the L2 loss, but there are other choices, like, for instance, the absolute value, or the so-called epsilon insensitive loss introduced by Vladimir Vapnik, and I think I may have, let's see. Yeah, so for instance, this is the quadratic loss, here is the error, and this is the absolute value, and this is the epsilon insensitive loss. And this is all in the cases of regression, which y can be a real number. Now, in the case of classification, when y is either 0 or 1, then I can have the other types of losses, which are, one is the hinge loss, which means you pay a lot. One, if you are wrong, your sign is wrong in your F, or you pay this is the analog to the square loss. You pay the square of your error. So y is 0, 1, and this is what you pay. And as you can see here, this hinge loss, which is the positive part of this error, 1 minus y times f, y times your prediction. If you look here, you see that in the hinge loss would be this kind of loss here. So they are all closely related. They're kind of one an approximation of the other. But for instance, when we see tomorrow this square loss regularization and support vector machines, the real difference, they are very similar to each other. The only difference is a different loss function that they use, square loss versus the hinge loss. And this gives rise to a different optimization problem, but the basic structure of the solution and the basic properties are exactly the same. So, now, how can I define generalization in a quantitative way? The key notion is the one of expected loss. So this is the expectation, this is the unknown probability distribution, this is my loss function, think of f of x minus y squared, for instance, and this is the probability distribution. If I would have the probability distribution, this is a measure of the expected loss, what I would expect in the future, in the average. And so this would be very ideal if I want to measure my future error of a function I have. Suppose I have an algorithm, I'm a hedge fund, I want to predict the market tomorrow, and this would be the expected value of, for instance, how much I'm losing or making tomorrow, right? So the error I'm making in the average in the future. The problem is that I don't have the probability distribution, as we said. So if I would have the probability distribution, of course, a good idea would be to find the minimum of that loss, to find the f, the function that minimizes the error, that it predicts best. This would give me what's sometimes called the target function, the minimizer of the error, the best function. Now, so these are, in summary, the distribution I don't know, the training set I label n because that's the number of examples we could change. This is the loss function. This is the expected risk. And this is what, since I don't know this, a proxy for it. Is the empirical, is what I can measure on my training set. I have these n examples, and I just take the loss, so the difference between the prediction, according to the metric, to the loss function I use, and the actual true value, and I take the average of that. Now, and using this, I could, using this proxy, I can measure this empirical error for a specific function, like, so I take an f, and I can try also to think, well, I could minimize it. That's the most natural thing. Look for the f that minimizes this empirical. Now, the key question is, if I want to do this, for instance, again, I'm a hedge fund. I found an F from past data about the stock market. I find that this is the error of the past. I find it's pretty good, doing well. But what I would like really to know before I bet $1 billion on this, I want to know that this empirical error that I measured is actually a good proxy for the expected. This is the kind of warranty that I want to know on my algorithm. I want to know that as I increase the number of data in my training set, the probability of the difference between the two being less than epsilon is very large. And of course, I would like to know, in reality, some bounds on n, for how many data I need to know to have in order to have this epsilon in that and that be good enough to bet $1 billion. Okay, so so it turns out that that minimization problem, finding the best f just from the empirical, minimize the empirical error, is actually not even not well defined. It's completely imposed. I have to define the space of function over which I do the minimization. What is the set of models of functions, of relations. And so this is called the hypothesis space. And the intuition is that I have to restrict this. I cannot allow everything to be there, right? I have to say which is the class of functions, of models, of theories. Turns out this is, restricting this appropriately is the key to making the problem well posed and simultaneously also to have predictability. Okay? So, for instance, I could restrict this space to be linear functions or polynomials. How many of you know what a Sobolev space is? Okay. In a Sobolev space, you define it in terms of norms of derivatives, bounds of the norms of derivatives. You don't really need to know, but I'll give you a little insight later. There is this tight relation between restricting the hypothesis space appropriately and smoothness of the functions that are in this hypothesis space. So let's look at this class of algorithms which are called empirical risk minimization, and I already described what it is. It's finding an F that minimizes the empirical risk, and the key is here is to define the space of function here, H, in such a way that the problem is well posed and gives you the function that can predict. So that's again repeating what I want. I want a function that minimizes this proxy for the expected error, is the empirical risk. And what I would like to have is generalization. So for the number of examples that goes to infinity, you want to have that this proxy becomes the same as the expected error. And I'll give you an example. It seems something kind of trivial, but it is not. In most cases, that's not true for H arbitrary. For instance, you'd say maybe if F is a well-behaved function, like continuous functions, that does not work. So you need something more in terms of which hypothesis space. So you want that, and you also, of course, well-posed essentially stability. Again, if I'm a hedge fund, I have used historical data on the S&P for getting this algorithm that predicts whether tomorrow will go up or down. And, I find that if I perturb a little bit, one of the component of my X vectors in the example, so for instance, one of the components is the closing price at 4 p.m. every day of the Nasdaq. That's one of my regressors. I perturb it a little bit, and the function I get out now as a predictor changes a lot. Well, that's very troubling because the closing price is quite noisy. So you want to have stability of your solution. And so this is really the key property of well-posedness that you want to have when you solve, for instance, your minimization. So, of course, you want to exist unique. These are typically, you can ensure those, but this one is not trivial at all, and it's key in learning. Those are the two conditions: generalization, stability. Here are examples. Suppose, again, is the one-dimensional case of function interpolation or approximation, actually. You have some sparse data, and suppose these are samples from this function. Now, suppose you have your algorithm giving this solution, And the question is, if I get more data, will it converge to the correct solution? This is a condition for generalization. That's a case where I have 10 samples. My hypothesis space is polynomial of the 10th degree. So it fits exactly the data because it has enough degrees of freedom. But when I perturb the points slightly, the solution changes a lot in certain points. It's very unstable. If I restrict, make this hypothesis space simpler, so now you have degree two polynomials, then I don't fit exactly the data, but the solution is much more stable when I perturb. So now this is an interesting question. There is a lot of learning theory, typically Ivanov and others, have been concerned about the problem of generalization, predictability. But independently, and so one of the conditions that is known guarantees generalization is for the hypothesis space to be compact. And I tell you in a second what it is. And it turned out that it was well known since Tikhonov that the same property guarantees well in many problems. So the question which was open until a few years ago is whether or not these conditions of stability on one hand and generalization on the other are related or not. It turns out they are equivalent under the appropriate definition of stability, which is, I find, very interesting. So if you ensure one of the two, the other is automatically false. Both of them. So, in a sense, it's easy to see in the case of let me see if I can let me give a feeling for. Okay, so if we look at this problem, one could think, how can I have an H space of function that could do a reasonable job, that could ensure stability and generalization. Let's say generalization. One could say continuous functions, but as you can see, I can make many, an infinite number of continuous functions go through those points. Right? So continuity by itself is not enough. Now, on the other hand, if I impose some condition of smoothness, the intuition is, if I, for instance, say that the interpolated function cannot have a say, a derivative which is higher than something at any point. Then the intuition is this may do the job. Certainly restricts the number of functions I can put through the. And there is this definition, this property of a space of function to be compact, and this means, can you see actually?
If you have a white chart.
Okay. That's a good idea. Thank you. So, so that's my space of hypotheses. There are function f in it, and if I have that f is uniformly bound, if for all x, all f are such that f of x is less than m for all x. Okay, they cannot be larger than some value. And then if I have that f is the space H is equicontinuous. Anybody knows what it is? Okay, you know what continuity is. So f is continuous if for any, let's say, any delta, there is an epsilon such that I can take x prime minus x2 less than delta, and then f of x is less than epsilon. Okay, and if this is true for, I want this to be true for all x prime and x double. Now, this is continuity. We saw it's not enough to impose continuity, but equicontinuity means that this is true for all f in the space, uniformly. So using the same delta and epsilon. That's the trick. Now, if you have these two properties, equicontinuity, so this is for all f, and boundedness, there is a theorem from Darzela that says that space is compact. Compactness essentially says that, this is probably the best way to describe it, connects the space to smoothness, to how smooth the functions in the space are. Because it's like saying that the derivative, they cannot change too much. And no function in the space can change too much. Right? Uniform. There is a bound for. Yeah.
So I'm a little confused. So the risk is an expectation, right?
Sorry?
The ERM is that's an expectation, right? And so you're looking for.
We're not speaking about minimization now.
Sorry, expectation.
Yeah, but we're not speaking, I'm just telling you which is the property of the space of functions, right?
Right, but
The hypothesis space.
So my memory is it's something like the weak star interval or something like that. Or like this isn't specific to learning, is it?
This is not specific to learning, but the condition for the empirical risk minimization to generalize. In other words, this condition here this, for instance, is guaranteed if you do empirical risk minimization in a space of functions which is compact.
Okay. And what you're doing right now is just trying to characterize which functions it's true that
I'm telling you what are, a property of the space, of a space of function which is compact.
Okay.
Space of function which is compactness is equivalent to equicontinuity.
Okay.
So that's a connection with smoothness. Why smoothness is important. Equicontinuity is very similar to, is essentially a smoothness condition on all the functions in space. Is that, you seem still puzzled.
Well, yeah, because like I guess I vaguely remember equicontinuity is one way of getting like convergence of expectations from finite. Like I'll think about it.
Okay. So, in fact, I mentioned this very quickly. The compactness is a condition which is sufficient for generalization, is sufficient also for stability, but there are conditions that are more general, that are necessary and sufficient, and this is a characterization in terms of what is called uniform Grigoryenko-Cantelli class of function. I just want to mention that you don't need it, not even for tomorrow. And there is a corresponding theorem that defines stability in a certain way, which I'm not going to tell you much about it, apart from the fact that it's something like deleting one of the training points and measuring how much your prediction changes. But that shows that the conditions, this condition of an hypothesis space being UGC is equivalent to stability. So ensuring stability and generalization are completely equivalent under these definitions. They correspond to the same constraints on H. They're both guaranteed by stability. So so now it's nice that you can get to those two conditions that you'd like to have in learning. So the ability to predict and stability with respect to the data, you can get them simultaneously. And you can look at either having a stable algorithm or restricting the hypothesis space in empirical risk minimization. And so, the kind of deep philosophical implication is something like this cartoon of what science is about. It's kind of starting with Newton, taking measurements of the apple falling, and try to find a law, a function that could fit the data and be predictive for future experiments. So the kind of learning theory, like Buckley or so, tells you in order to do this, in order not to simply fit the data but also be predictive, you need to restrict the space of possible models theory before you see the data. Okay? Only then a theory can be predictive. If you just fit the data, then you're doing astrology, but not astronomy, right? You're just explaining the data. That's often what the financial newspapers do. They tell you, today the market went down because people sold, basically. And that's not something you can use to predict tomorrow. So, but the other part of the results tells you, theories should be stable. So what does that mean? Is that if you add the new data, they should not, most of the time, they should not change much. So in other words, you cannot expect relativity theory to come very often. These are kind of tautology. Since science has to be predictive, then it cannot be violated all the time. So there is this close connection between prediction and stability. Now, tomorrow you hear about regularization, and Ma spoke about regularization, Tikhonov regularization. This R of F is a functional that you minimize together with the empirical risk. And one way to look at it is to think of minimizing the empirical risk, DRM, but under some constraints on the hypothesis space, right? For example, it could be the norm of F, this R of F. And so one way to solve a problem like this is to use Lagrange multipliers, which means minimizing something like, turns out Tikhonov is not exactly the same as completely equivalent to Ivanov. There's something, but that's one way to look at it. And so this is the connection between minimizing the empirical risk under the constraint on the hypothesis space and looking at Tikhonov regularization as a way to do this.
So, sorry, can I just ask, this is probably a clarification for myself. So basically what Ivanov regularization is doing is saying there's this hypothesis space and some parts of it are verboten, and therefore the parts that remain will ensure stability. Whereas Tikhonov is saying any part of the hypothesis space is possible, but the complexity of the hypothesis in a way is going to penalize you, pushing you more towards the stable parts of the hypothesis space.
Yeah. But, just from the point of view of optimization, one way to solve this constraint problem is to solve this, thinking of gamma as a Lagrange multiplier. And then and then and solve for, right? So
I can see now.
there are other there is another interpretation that was mentioned before in terms of probabilistic interpretation. This is related to the prior on F, and this is a model, a probabilistic model of your measurement process. In that sense, you know, this would correspond to harder constraints. It would be easier to see the probabilistic interpretation here. Okay, so so that's essentially summarizing what I just said. You know, Tikhonov regularization and Ivanov ensured well-posedness, especially stability, and ensures generalization, and there is this close connection between ERM on a constrained hypothesis space. The story, of course, is that you have to put some constraints in order to solve the inverse problem. You have to put some constraints in order to solve the problem of learning. You have to put some constraints in order to get generalization. Constraints may be a lot of different things. It turns out that, you know, if you have very specific constraints, like for instance, you know that you have a linear mapping between input and output, that's a very strong constraint. You should use it. But if you are, you know, ignorant, then there are these minimal constraints you have to assume if you want to generalize. So, by the way, generalize, I should say that, does not mean that your solution is good. Generalization means that the empirical error, what you measure on the training set, is a good proxy for what will happen in the future. So, if I'm the hedge fund, I have to find an algorithm that works well on my data, and I want to have a guarantee on this type of algorithms that in general, then I will know that my small error training set will be within a certain probabilities, small error in future. But generalization does not guarantee that automatically what I find is a good predictor on the empirical side. I have to measure, but that's easy to do.
So is this the same sort of distinction between precision and accuracy?
No, it's more a distinction. You know, one of the standard preoccupation of all the statisticians is consistency, universal consistency. And this means that in our case, this would mean that our algorithm converges to the best possible solution. You can have those guarantees here, but I think in practice, that's my personal opinion, much less important than generalization. Because I can measure the error in the empirical, and I do in practice all the time. What I need to know is that this is a good proxy for the future. That's generalization, it's not consistency. Okay, I think we have a window for lunch, which is 50 minutes. So probably better to stop here. But if you have some questions, urgent questions, ask them now. Otherwise, we'll be around for the next